If you toss a hammer into the air, it doesn't spin around its handle, it rotates around its heavy head. We intuitively think of objects as having a single universal middle, but assuming a shape has only one center misrepresents the way mass and geometry actually interact. In physics, there are three distinct centers at play. The first is the centroid. This is the geometric center of a shape's area or volume. The calculation for a centroid is independent of mass. It reflects only the geometry of the space the object occupies. The second point is the center of mass. Real-world objects often combine materials of different densities, like a light wooden handle and a dense steel head. That non-uniformity drags the true balance point toward the heaviest section. The third is the center of gravity. It tracks the weight-weighted average location, reacting strictly to the downward pull of an external gravitational field. These three terms are frequently used interchangeably because, on Earth, our gravitational field is functionally uniform. For an object made of a single uniform material, the shape, the mass, and the weight all converge into a single location. However, precision is required to solve advanced physical problems. Whether predicting the spin of a satellite or designing a skyscraper, engineers and physicists must decouple these three concepts to isolate the geometry from the weight it carries. To find an environment where the center of mass and center of gravity physically separate, we have to look beyond terrestrial engineering to the scale of orbital mechanics. In the Earth-Moon system, gravitational fields are no longer perfectly uniform. They project as gradients over thousands of kilometers. Because gravity weakens as distance increases, the side of the Moon facing the Earth is subjected to a stronger gravitational pull than the far side facing into space. That uneven pull exerts an asymmetric force on the Moon's wake. It drags the center of gravity away from the Moon's center of mass, shifting it closer to the Earth. Two orbiting bodies revolve around a shared center of mass called a barycenter. For the Earth-Moon system, that shared pivot point is located roughly 1,700 kilometers beneath the Earth's surface. Because that anchor point sits far away from the Earth's own geometric center, our planet oscillates in its orbit as the Moon circles around us. Astrophysicists track these diverging centers to maintain satellite orbits. Conversely, structural engineers assume gravity is uniform to isolate the unmoving geometric centroid of the steel and concrete they use for construction. This diagram illustrates the mathematical process for locating that geometric center. Establishing the balance point of an irregular two-dimensional shape requires calculus. The area is sliced into an infinite number of differential vertical strips, each with a width denoted as dx. The x-coordinate of the centroid is the area-weighted average of the distance to every infinite strip. The formal definition integrates the distance of each strip across the boundary, divided by total area. Repeating this with horizontal strips establishes the y-coordinate. Continuous integration provides a rigorous proof for a shape's center. But physical infrastructure is not constructed out of continuously curving calculus boundaries. Structural engineering requires a discrete tool to rapidly analyze the standard steel beams and concrete profiles used in modern design. To bypass the need for continuous integration on every component, statics relies on the method of composite parts. This relies on the principle of superposition. Instead of analyzing a complex cross-section as a single curve, engineers fracture it into primitive geometric building blocks. Primitive shapes like rectangles and triangles have pre-calculated local centroids. Their geometric centers are established constants. By multiplying each part's local centroid by its area, summing those results, and dividing by the total area, you produce the single global centroid for the entire beam. This discrete math also allows engineers to account for physical voids, using the concept of negative area. If a beam has cutouts or drilled holes, the area of those voids is treated as a negative value. Subtracting them from the global summation accurately shifts the centroid away from the missing material. Establishing this coordinate is the prerequisite for all further analysis. An engineer cannot calculate a beam's moment of inertia or its resistance to bending until the geometric centroid is identified. The composite summation method successfully translates the abstract rigor of calculus into a practical framework for structural design. Locating a centroid establishes a point of balance. Moving that centroid allows for the calculation of volume. Pappus's centroid theorem is a principle that connects two-dimensional area directly with three-dimensional volume. Sweeping a two-dimensional shape around an external, unmoving axis generates a solid of revolution. The theorem states that the generated three-dimensional volume is exactly equal to the two-dimensional area multiplied by the distance traveled by its centroid. To find the volume of a torus, you take the area of the generating circle, pi times radius squared. Then you calculate the distance the centroid travels along its circular path using the circumference equation based on its distance from the external axis. Multiplying those two variables yields the volume of the torus, bypassing the need for complex triple integrals. The centroid acts as a geometric multiplier. It translates two-dimensional data into three-dimensional volumes by leveraging the symmetry of its path. The principles governing an I-beam and the mechanics of orbits share the exact same physical hierarchy. In deep space, navigating gravitational gradients requires mapping how a center of gravity shifts away from a center of mass to predict trajectories. Terrestrial architecture relies on gravity and material density being consistent enough to be treated as uniform. This environment allows engineers to collapse physical mass and weight into pure geometry. Selecting the correct center to analyze dictates whether a physicist accurately lands a satellite or an engineer successfully builds a bridge. Intuition points us toward a general middle, but structural and cosmic stability require mathematical rigor. Isolating the centroid allows engineers to apply calculus, leverage composite summations for structural beams, and calculate 3D volumes using Pappus's theorem. The constant forces of physics, structural load, bending, and orbital motion will continuously interact with an object through these specific anchor points. The integrity of a design depends on these mathematical centers. Mapping them is a critical step in turning geometric theory into functional engineering.